Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today I will be doing section 1, question 1.11. This question asks us to show that the ideal generated by the curve t cubed t to the fourth t to the fifth is a prime ideal of height 2 which cannot be generated by two elements. Now, this is difficult for two reasons. The first is, how do you find a generating set? And the second is, how do you show that an ideal cannot be generated by two elements? Now, there are elementary techniques which I employed to find both and found them challenging. There was it, all of my algebra just sort of exploded, and all of my arguments exploded. However, I have picked up David Eisenbud's commutative algebra and brought up commutative algebra section. Goodness, that section mark is not very good. Section 15. Specifically 15.10.4 and I believe 15.4. So this contains what is called Buchberger's. I'm sorry, I can't pronounce German. Buchberger's argument, and this is the actual engine by which I found uh, a generating set. Now, I'm not going to go very into it. Essentially, it is Gram-Schmidt, but significantly more labor intensive. However, it finds you a generating set of an ideal. In fact, given an ideal J within K adjoin X, Y, Z, adjoin alpha 1 through to alpha to the R, one can find a generating set well, Grobner basis of J intersect K X Y Z. Now, if we shear off the 2 up to R, then our I of Y is actually equal to the following. Z minus t to the 5 intersect K X Y Z. Now this is within K X Y Z adjoin T, and so we will use I used Buchberger's algorithm, starting with this and the elimination order T, well, the following elimination order is greater than x to the beta is greater than y to the gamma is great y to the gamma is greater than z to the delta, i.e. tx cubed is going to be greater than x to the 56, but this is going to be greater than yz y to the 12z, which is itself greater than z. Now, using this elimination basis, the Grosvenor basis of I, our greater ideal, x minus t cubed, y minus t to the fourth, z minus t to the 5, the elements of the Grosvenor basis which don't include t are going to be are going to form a Grosvenor basis for I of y, which I have the full list of the Grosvenor basis of this. So it starts with x minus t cubed, y minus t to the 4, z minus t to the 5th. There's 10 elements in it, so t x minus y, t y minus z, x squared minus t z. What is next? xz minus y squared, xz minus y squared, yz minus x cubed. Now, z squared minus xy, x squared y, z cubed minus xy cubed, and finally z to the 4th minus y to the 5th. Now, not only does this bit form a Grosvenor basis of I of y, but if we wanted to remove our variable x as well, then this bit would form a Grosvenor basis, although rather a generating set for I of y intersect k x y. Now, I just want to quickly give some sort of a very quick introduction to Grosvenor bases. Uh, one can guess from this what an initial term is. It is written IN with a order sign because it is with respect to this order. With respect to a different order, it would obviously be different. So, for instance, z cubed minus xy cubed. Well, that would be xy cubed, etc. Now, the ideal generated by the initial terms of every ideal is called the initial INI. Now, the initial terms of all of these forms a basis for INI. Well, INI of y. And the initial terms of all of these form a basis for, well, the initial terms of these form a basis of INI of y, and the initial terms of all of them form a basis of this, of the initial terms of this, of the ideal generated by the initial terms of every element of that. That's what the additional property that the Grosvenor basis should represent is. However, the property which I am interested in is that this forms a generating set for I of y. Now, we can shear off this, and we can shear off, let me find which ones. Ooh, I did definitely write it somewhere. Is it on the other side? No, it is not. Hmm. Aha. Yeah, and we can shear off this one. Therefore, I need to qualify why we can shear these off, obviously. So, z to the fourth minus y to the fifth is equal to y cubed times by xz minus y squared plus z times z cubed minus xy cubed. So we can shear this one off because it's within the span, so it doesn't actually add anything if it's within a generating set. Now next, z cubed minus xy cubed is equal to xy multiplied by xz minus y squared plus z multiplied by z squared minus x squared y. So we can shear off this. Therefore, if these 5 elements form a basis, and they do by the fact that they satisfy Buchberger's criterion, because I used Buchberger's algorithm using a starting point of this and a set and a monomial order this. Now, xz minus y squared, yz minus x cubed, z squared minus x squared y equals I of y. And we have found the generating set. Now that was, on my end, like 2 days worth of work just performing Buchberger's algorithm because it was a new algorithm to me and I wanted to make sure that I could do it. I basically you have to test pairs of elements against one another, and if that test fails, you add it to your eventual list, and then you need to test all the pairs of elements, including that new thing. And right at the very end, as I was just about to do the very last 2 pairs, uh, I got given this. And then again, I got given this, which meant that I had to do maybe 20 more basic calculations. But I of y is equal to xz minus y squared, yz minus x cubed, z squared minus x squared y. Oh, and feel free to pause when I gave the linear relations on this and this linear. The relations on those two. You can check my work to see if it's correct. But I have done that maybe triply over. Now, suppose it were generated by u, v, and k, x, y, z. Here is where I'm using things from section 2 of chapter 1 of Hartshorne. I am well, no, I believe it's actually section 5. Let me just double check. It's page 50. I know that for sure. Section 7. I'm using the graded module structure of a homogeneous ideal. Suppose it were generated by two elements. Then we can define U to be equal to UD plus everything else, V to be equal to VE plus everything else, and the degree of UD is D, the degree of VE is equal to E, i.e. these are homogeneous elements of degree D and E, respectively. As the as the linear part of I of y does not exist, D and E must be greater than 1. What that means is every single one of these generators, the that contains no linear parts. And by linear parts I mean x, x plus y, x plus 3y minus z, etc. I of y contains nothing of the sort, so D and E must be greater than 1. Now, here is where my notes become patchy. The degree 2 form of any element of I of y must then be in U, D, V, E. What I believe that is saying is because F equals F2 plus F3 plus dot dot dot, where each of these are homogeneous of degree 2, 3, etc. The F2 cannot be K, X, Y, Z linearly found by this or this because their degrees are at, because U prime is equal to U of 3 plus U4 dot dot dot, same for V, and these can be empty. They can just be U3 is 0 because the degree of 0, by convention it's negative infinity, but in reality it's homogeneous of degree anything you want because of how degrees really work. Basically 0 is within R of D, where R is the direct sum of some abelian groups. All of those abelian groups contain 0, because that's how direct sums, well, that's how coproducts work in category theory when you're working over groups or rings, or you want to glue together all of the various identity elements, or the additive identities. But anyway, f is f2, f3, etc. U dash is u3 plus u4, etc. And you can't multiply by any element of k, x, y, z to get this equal to this, or this equal to this, etc. You can't even like go downwards, like cancelling things out. Therefore, F2 must be within UDVE for now. So, xz minus y squared is within our UDVE. Yz is within UDVE, is within the ideal generated by the initial homogeneous form of U and V in proper terms. And finally, z squared is within UDVE. Therefore, xz minus y squared yz z squared is a subset of UDVE. Now, I won't prove it here, but these are linearly independent, and so we can conclude that the span of three linearly independent elements cannot be a subset of the span of two linearly independent, linearly dependent, it doesn't matter, that elements of kx, y, z. Therefore, we have reached a contradiction. A contradiction as the former is linearly independent. I believe that you can also I can back this up by saying we're working over two K modules, which means that these are both vector spaces. So linearly independent actually genuinely means that this can't be a subset of this. If we're working over some arbitrary ring module, I'm not sure if this would still hold, but it definitely holds over K. So therefore I of y must be generated by more than two elements. Thus we have shown this bit. Now we need to show it's a prime ideal of height 2, which is not horrid. So, firstly, I of y is the kernel of the ring homomorphism from k, x, y, z into, not maps into k of t such that x is mapped to t cubed, not x cubed, t cubed. I thought that it could possibly look like a t that's been knocked over or something. T cubed, y maps to t to the 4, z maps to t to the 5, and then r in k maps to r in k. I.e. this is truly an evaluation. Therefore, by the first isomorphism theorem, A of y, not I of y, the domain over the over y, I of y, or yeah, the domain over the kernel is equal to the image, or isomorphic to the image, which is k adjoin t cubed, t to the 4th, and t to the 5th. which as a k module is k up plus t cubed k up plus t to the fourth k dot 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 dot. But a of y is a subset of k of t, k adjoint t, which is an integral domain. Therefore, a of y is an integral domain, and I of y is prime. Now, let me see. Okay, this is a very cheaty way of doing things, but 0 is a subset and not equal to t cubed t to the fourth t to the fifth, which is a subset of k, well, a of y. I'm not sure if it's meant to be blackboard A. I know that the affine space is meant to be a blackboard letter, but I will just stick with what I'm doing. So the dimension of A of y, which is the supremum of supremum of chains of distinct prime ideals within A of y, is greater than 1. Now, 0 is a subset and not equal to xz minus y squared, which is a subset and not equal to I of y. So the height of I of y is greater than or equal to 2. Now we have, by I believe theorem 1.8, but I will just write it out fully. The height of I of y plus the dimension of well, a of y is going to be equal to the dimension of not this, the dimension of k adjoint x, y, z, i.e. greater than or equal to 2 plus greater than or equal to 1 equals 3. The height of I of y equals 2. Therefore, we are done because we have shown that I of y is a prime ideal which is of height 2 and cannot be generated by 2 elements. Therefore, what has what what was to be demonstrated has been. So I can confidently say thank you for watching. Now, I also want to say Buchberger's algorithm slash criterion, and also Grosvenor bases and also, I believe, elimination theory, but I have given enough context by which one could very easily recreate my proof. Therefore, I am done. I did also want to say one last thing, which is I am almost completely certain this is not the proof that Hartshorne had intended. I think that what Hartshorne had intended was that one might just skip over this, or just have a really big go at it as an example of some question which we can't yet answer, but will be able to answer at the end of the book. But no, I think that that was a very mean question to put at the very end of the first section. However, it is done now. I have done it. Goodbye.